Good morning, my dear professors. Good morning, my dear friends. Good morning, everybody. My name is Ho Si Tang, and today I'm very honored to present to you my graduation thesis, namely Robustness of Human Detection Models with Deep Learning. My presentation consists of 5 parts. The first part is about the big picture problem, fallen human detection. The second one is about the types of approaches to this problem that have been tried. And the third one is about the failures when applying these solutions. The next is my solution to that problem. Lastly, we're gonna conclude about what have been done right and what could be improved. To begin with, I'm talking about the problems where we have to predict the presence of human inside the photos. At in Ria, where I've been doing my research in my internship, uh, a new dataset has been collected for training and fine-tuning a mobile robot to detecting humans in the images in which there are a lot of images, including humans who have fallen down to the ground. These are all still images. We have dataset for videos as well, but my research is only about still images, 2D ones. There are many solutions to this sort of problems, and we have tried many of them out. Here I could list our three solutions that we have tried with this newly elaborated dataset. The first one is mask RCNN. As the latest generation in the RCNN based algorithms, mask RCNN has the ability of the same faster RCNN, which is to predict the bounding box and the label for each object presented in the image, and at the same time it has the ability to provide this instant segmentation for that object as well. And here's an example on the Coco test set. OpenPose, on the other hand, does it in a different manner. It predicts the key points or the part of the body which is very close to the skeleton system of the body. This is very similar to the Kinect, a device of Microsoft, both Kinect V1 and Kinect V2, but they are quite different. The Kinects have the depth sensor, while OpenPose will only with 2D images. Now, OpenPose is also very highly applicable in real life as well, because it can run at around 26 frames per second with a system equipped with a GTX 1080 Ti, and it could be improved in the future as well. The last technique is YOLO, which stands for You Only Look Once. The goal of YOLO is the same as the mask CNN, which is to predict the bounding box with a label for each object in the image. On the other hand, YOLO is super fast. While mask CNN can only run at around 5 frames per second, YOLO can run at around 330, 54, or even 90. 120 frames per second, depending on the configuration. In exchange, YOLO is a little bit far below in accuracy. How does YOLO do this so fast compared to Mask CNN? Because it does this in only one phase. It regresses the areas containing the object by using a grid S by S since the beginning, while Mask CNN does it in 2 phases. The first phase is to pull the areas of interest, and then the second part is classify that area. Unfortunately, when applying these sort of obvious solutions to this problem, because this is a sort of sub-problem of the bigger one which has been solved over the years, we have observed bad results. On the initial image on the top left here is an image with a model putting on the ground pretending to be the fallen human, and OpenPose failed to work with that. Only until we change some orientations here by rotating the image to kind of 25 degrees, 90 degrees, 140 degrees. It works best with a pose where the human is in upright position, and it does not work with every rotation. The same story happens with YOLO as well. YOLO happens to be the worst solution here when it comes to accuracy, because it sacrifices that for speed, and the same story happens where YOLO works best with the images rotated to where a human is at upright position. And the most surprising one is about Mascar CNN because it's supposed to be the best overall technique here with the best accuracy. It doesn't predict anything from all the images or rotations we've tried. Well, one of the spontaneous solutions to this problem is to rotate the image, the input image, to enough rotations, fit all of them through the network, and summarize the results of the network through all the rotated versions. The downside of that is that the system will be super slow, because instead of processing only one image, the system has to run X time when X is proportional to the times we rotate the image. Here, we rotate it 4 times, we process the model 4 times. That's super slow in case of sort of OpenPose or Mascar CNN. And at the same time, this doesn't change the nature of the CNN that is not invariant to rotations. What could be the reason for CNN not being invariant to rotations? Maybe the images haven't been augmented enough. As I've been observing in each training technique, they all augment the images before training. They flip the image horizontally, vertically, they crop the images, and they rotate the image to a random angle between -40 and +40 degrees. But that is where the problem comes in, because with all that, we still lack 5 degrees from 40 to 45. It really somewhat meaningful if we rotate to a random angle between -45 and +45. That is not the only thing, because the algorithms themselves, they rotate the image to that degree and they feed only the rotated images to the network, and the network only learn with the rotated version, which is only one direction. Well, we have a lot of directions. What if the image is rotated to another one? The story is different. The second reason is because naturally CNNs aren't invariant to rotations. With the help of pooling techniques, with the help of sliding windows and filters, CNNs are only invariant to transformations and resizing, but they aren't invariant to rotations. And I'm more biased towards the second drop, and I'm work with that. But before I'm talking about my work done here, I would like to introduce about the algorithm that I chose to work with. I listed out 3 of them, but I had to choose one because I don't have enough time to experiment to all of them. So I chose OpenPose. The reason is that OpenPose predicts the key points on the body and could be applicable on the images where the humans are occluded in the images. And this is the pipeline of OpenPose. It takes the whole image as input, and it predicts the part confidence maps for all the parts of the body and the images, and also the part affinity fields. The part affinity fields is the 2D vector fields predicting whether 2 parts belonging to the same limb, and then they will do some sort of localization so that we can predict the limb for each person inside that image. Because in the image, we have a lot of people, and in one person body, we have a lot of parts as well. And after that, we have the result as on the E photo here. The network compose contains 7 stages. The first one is 10 first layers of BGC19, which have been well pre-trained and fine-tuned on ImageNet. And after that, we have 4 stages to predict the part affinity fields for the image. The last 2 predict the confidence map for the image as well. Well, but I will be only working with BGC because I believe that if I can feed the network with more meaningful information by alternating the first layer of the first stage here, the first layer here at 3x3 convolutional layer here, it will be very meaningful to the network. The first approach that I tried is to alter the filter of the first layer by using image gradient. Like these two examples on the right here, the gradients of the image have tend to go from the lighter pixels to the darker one, and that make the bound between the dark and the light, and also between the places with different colors, which is very meaningful. I mean, not only colors but levels of light as well be meaningful to the network. And how do I approach these directions? That's by using um, the formula on the left by calculating the gx and gy, then calculating computing the theta by using theta equals arctan of gy divided by gx. For example, here if theta equals 135 degrees, the cone will be rotated to 135 degrees like this. But unfortunately, this doesn't work out the solution because my code hasn't been well optimized. And if I wanted to train my unoptimized code, it would take me 2 months to train a system through 60 epochs, which is super long, and I couldn't afford that much time at the moment. So I went towards the second solution using deformable convolutional networks. In the original paper, it was recorded that um, this thing has improved the RCN-based algorithms by a margin. It worked out on the two-phased techniques, but I haven't tried it yet on a both. That's why I wanted to give it a chance. What this thing does is it feeds the filters or the weights through a convolutional network and train them so that they could be adaptive to the feature maps as well, which is a bit similar to what I've tried, but this thing is more adaptive, more flexible, because instead of just rotating that, the filters could be anything, could be anyhow, in any shapes. These are three um, custom um, deformed kernels that might be learned through the network. So I replaced the first two layers with two layers from deformable convolutional networks. Unfortunately, the system doesn't reach the point of improvements. It doesn't even lower the performance of the network from 54.6% to 43%, which is not acceptable at all. The system stopped converging after epoch 25, so I had to shut down the system. I had no time to see whether what I did wrong to appear, because after collecting the result, I continue applying another method, which is the third approach here I'm introducing to you. By using 8 rotated channel limits as input, instead of using 3 channels of red, green, blue, I combined all of them together to make a grayscale channel, and I rotated it to the other 7 orientations, like 8 orientations on the compass. And then I stack them together, feed them to the network. And that made some sense. After the first 60 epochs, the system kept converging. I kept training it for another 100 epochs, and after the 42 for the second one, a second session, which combined to be 102 epochs on the both sessions, the system has reached a point where it surpassed the original one with 55.2% versus the first model with 54.6%, which is a bit of an improvement, even on a margin. So I'd like to give some conclusions about the work that I've done. The third approach has brought about some good insight. It improved the model, but not too much. But it just taught me that additional good information on the input is very meaningful to the network. On the other hand, I've done something not quite effective here. The first model hasn't been well optimized, and I think I could do it in a better manner by improving my NumPy combinations with the PyTorch model so that I could train it in a much shorter time. The last point is about the second approach, where I think I did it in the wrong manner as well. In the paper, they pointed out that this is better applied at the very last convolutional layers of the network, while I applied it on the first ones, which is also not good in theory because the first layers are very crucial to the network. It provides very good information about the edges and the colors of the image, while here I changed them all. I didn't even use the restraint weights, so I think that's why. Oh well, I will as well change that for another attempt in the future. There are many things could be done with the success of the third approach. I used the system with only grayscale images because I thought that detecting human or objects in general relies very much on the edges and uh, not the color. So I used grayscale so I could reduce the workload of the system. But unfortunately, when retraining the original system to compare the system on grayscale images, because the system was trained on RGB, so the system dipped the performance from 61.8% to 54.6%. I surpassed it, so now I apply RGB to see whether it could surpass the 61.8% on the original one with RGB images as well. This thing has been put on the system for a week till now. I will finish it in a couple of days and I will check whether that works. Also, rotations aren't the only thing we can put into the system alongside with the original images. We could also use HAR, histogram of oriented gradients. This thing is much like the image gradient on the first approach I tried. This could be very informative as well. And lastly, maybe number 8 is not the ultimate solution. We could experiment with different numbers to find out which one suits the best. And that is all about the work I've done during my internship at INRIA. Thank you for showing by and thanks for your attention. I owe a lot to my tutors here, both in Vietnam and my tutor in France, Mr. Dominic Freitas and Mr. Dao Chung Kien, so I could finish my thesis on time, though it hasn't actually finished yet. Some work hasn't been done. It's only 3 months in. This is what I've done, and thanks for your attention again.